Okay, so thank you, Sam and other organizers for inviting me here. It's a real privilege to be here, actually. So what I'm going to tell you a little bit about are these topological phases, and I changed the title invitation because Sumati is going to give the real deal to you, right? So I'm just making sure that you definitely come for her talk and you will get much more knowledge than what I have to say. Okay, all right. So I want to thank two young people. One is Adip Agarwal, who is sitting right there, and Arijit Haldar. And actually much of the stuff that I'm going to tell you, I learned from these two gentlemen. And actually one of them should be giving the talk here, actually, to be honest. Okay. And I've been very generously funded over the years by several funding agencies, and I'm very grateful for that. Okay. So phases to phases. So when I say phase, what do people understand here? So that's what a phase is, right? Right? That's what you would think a phase is, right? And I'm going to claim that something as innocuous as this, right, actually gives rise to all of this stuff, right? These are the phases of many electrons. So I'm going to try and tell you how this happens in some way, okay? And I was under the impression that this audience is going to be very diverse, and there are people who do condensed matter, there are people who do other areas of physics. My condolences to them, as you will see that, that's not the cool thing to do now. This is the right stuff to do. But nevertheless, so what I'm going to do is, I'm going to start assuming that you have not seen any of this stuff before, and just start from the real basic, maybe a slightly historic perspective. And then I will develop, in some sense, level by level. So first I'll give you what is this game about phases, what is all this story about. And then I'll tell you a little bit in a very illustrative, simple model, where this topology comes up in phases of electrons. And then I'll tell you something called the tenfold way, which is already advertised here. And then I will advertise some of Deep's work on topological phases and amorphous systems, and this I may just run through it very quickly. And then I will briefly mention what we have not discussed and some of the open issues, and I will also point out some of the topics that Sumati will cover in depth, okay? And I will do that as I go along, because we just communicated this morning and she indicated to me what she's going to do. So I may from time to time tell you what are the points that she may bring out more clearly than what I am discussing. Okay, so topological matters, right? So the Nobel Prize in 2016 was given to these three gentlemen. So you may actually wonder why listen to this talk, because the Nobel Prize for the topic has already gone, right? It's kind of too late, right? But I'll try to convince you that maybe there's another one down the line, so it may be worth hanging around and trying to do something, right? Okay, all right. So let's just start with phases of electrons. Okay, so we are taught in high school that matter broadly appears in three distinct phases at our scales, at least. So there's the solid, liquid, and gas phase. And, people have thought about this problem for many centuries and millennia, actually. So, there are, ancient India, there was this idea that everything is made of 5 elements. And it turns out that that's not just in India, and many other civilizations, these ideas came up that there are some elements that make up stuff. Right, but if you sort of try to do a very quick survey of how ideas evolved, I think the central step forward in our current understanding of matter and stuff on our scales goes back to Dalton. And I think his work was much earlier than other people, it appeared much earlier in the intellectual development of other people, because they didn't actually appreciate it at that time. So if you look at Wikipedia, this is actually a slide from his paper. And he actually pointed out that if you make this hypothesis, you can actually understand many compounds and so on. And he actually made pictures of them, way ahead of his time. And my understanding, based on very minimal reading of history, is that the physicists, the so-called physicists in those days, actually didn't take this very seriously, right? And it was not until the 1850s or so, people started taking this seriously and trying to build theories out of this. Yeah. Kelvin is a little later, no? That's much later. That's roughly 100 years later. So all this idea of loops and so on. Yeah. That's much later. Yeah. So roughly 100 years later. Yeah. Okay. No, but it's quite remarkable. I mean, it is way ahead of its times, right? Okay. Okay. So if you again look at someone who tried to start from this hypothesis and try to explain how do I get liquids, gases, and solids, I think I would say van der Waals is the first one who actually sort of nailed it, right? Yeah. Ancient Greeks. Oh yes, I had, okay, yeah, I don't know much about it. Actually, I know more about the Indian side of the story, right? Actually, Jayant can tell you more about it, he's the expert. So there's a person by name Kanada in India. So he actually had a very strong atomic hypothesis and he made many things, predictions and so on. I think there was a school of thought which didn't agree with him and so on. So actually maybe you can talk to Jayant about this, yeah. But yes, I mean, the Greeks had many people have different sort of elemental things that start many different civilizations, yes. Yeah. Okay, so in the modern era, if you look at it, I think it's van der Waals who actually started this game of, with the main idea that you had to have some interactions between these particles to actually get distinct phases. And actually he made a beautiful theory which is now standard textbook material, and in fact he got the Nobel Prize, one of the earliest Nobel Prizes to be awarded for this work. And it's actually a central sort of idea in physics. So the main point is that interaction between constituent degrees of freedom and in large numbers is what actually gives you phases, distinct phases. So that's what I would say is the message from van der Waals' work. But then you see, you have solids which you think is a phase of atoms. But then on this table, you have a solid which is a metal, which conducts electricity, and then you also have something which is an insulator. So solids themselves, although they have some characteristic of stiffness or something which may make them called solid, they have other characters which don't seem to agree with each other, right? So different solids can have different characters in the sense of conduction of electricity, right? So then people started thinking about this, and there was actually no theory for it for a long time until Thomson discovered the electron, right? And then very shortly after that, there was a beautiful theory by Grad, which used the picture that electrons form a classical ideal gas, and was able to sort out a very old puzzle, old in those days. So there was a 50-year-old puzzle in physics, which was the Wiedemann-Franz law, which showed that the ratio of the thermal conductivity divided by, the thermal conductivity divided by the electrical conductivity times absolute temperature is a universal number. By universal, I mean, it doesn't depend on which metal you're doing this measurement on, right? So this is what was not understood, why this was happening. And then Grad, of course, made this theory based on Thomson's discovery. And then there was a small problem. So it's an extremely successful theory in that it explained a 50-year-old puzzle. However, there's a small problem that this theory to be consistent required that 3 is equal to 9 by 2, right? Which is not true for usual values of 3, 9, and 2, and for the usual meaning of the divided by symbol, right? So there was a problem. There was a serious problem, right? So the theory is correct, it is ridiculously wrong, right? And so to sort this out, an entire new machinery had to be discovered, like what nature is doing at very small scales, and that is quantum mechanics. And now I'm going to zoom right up to, fast forward to current times, and I'm going to introduce you to the modern era, if you like. And this area where we look at many particles, but take into account their quantum mechanics and the interactions between them. And this is what we call as quantum condensed matter physics. And that field is what kind of looks at the problem of phases of electrons. So the punchline I want to give you is that the insulating phase that you see, you can view it as a solid phase of electrons. And that idea can be made quite precise, actually in what sense it is a solid. And the metallic phase of electrons, you can think of it as a fluid phase of electrons, where the electrons flow like a liquid or fluid generally, right? So that's the idea. And then the question that one asks is, in some sense, what are all the distinct phases that electrons can have? So of course, if it's a 3-mark question, the answer is just 3, solid, liquid, gas. But and we actually believed that was the case for a long time, right? And that is what has changed in the last, say, 15, 20 years. And that's what this whole talk is about. So I'm going to try and give you a flavor of what people have discovered in the last 10, 15 years. Okay, so the question is the following. So just like we change pressure and temperature and so on to get different phases of atoms, what one can do is one can sort of imagine that the large number of electrons in a system, in a material system, let's say, or maybe neutron stars. In fact, neutron stars are the best place to learn condensed matter physics, because as you start from the outermost atmosphere of neutron star, which is all of 0.5 microns thick, right? That's the atmosphere of the neutron star. And then you come down, you will see that all these different phases of fermions will be realized. Some people have actually believed there are these topological phases that are inside neutron stars. It's quite amazing. And as you go down into the depth, you actually see all the distinct phases of matter. So perhaps, we should actually just get astrophysics and tell them that, they're actually doing condensed matter. Right, in any case, okay. All right, so this is the point. And so the idea is that they see many different kinds of interactions. And just like you change pressure and temperature, etc., you could try and change some of these parameters, let's say. And as you move in this space of Hamiltonians, you would realize distinct phases of these electrons. And the question we are asking is, can we tabulate what are all possible phases of electrons without actually worrying about where these interactions come from? So that's the question. That's the real, that's the bottom line question of physics. And if I will make this point, if you look at, as we go along, that if you look at much of technology today, it actually relies on exploiting features of different phases of electrons. Okay, so what is the traditional wisdom in this game? So much of this wisdom that I'm pointing out here was actually taught to us by Landau. So Landau pointed out that if you want to classify distinct phases of many particles or many degrees of freedom generically, you can use symmetry as a classifying principle. So if you take a magnet, for example, like a ferromagnet, the magnet actually breaks the rotational symmetry of the underlying spin system, right? The spin system's Hamiltonian is such that, it doesn't matter which way you can actually rotate the full universe, and it's a symmetry, and that's basically what you have as a basic symmetry, but the state that is realized, which is the ferromagnetic state, it breaks that symmetry. So that's an example, right? And if you look at other phases, say for example a metal and a band insulator, you will see that there is no distinction between symmetry of these things. However, they are distinct because one has a liquid-like property in that it has a DC conductivity, whereas the other one has a zero conductivity, much like a liquid has zero shear modulus, whereas a solid has a finite shear modulus. So that's the connection. Yeah.
Coming from the soft condensed matter.
Yeah, sure.
Is there anything like viscoelasticity in like something between a liquid?
Of course, right. I mean, so for example, the conductivity has imaginary part. I mean, it has. So that's the viscous part. Yeah. Yeah. So there is. Yeah. You can put this all in the same framework actually. Yes. Yeah. Okay. So what do we believe are the phases, right? So if you do a typical grad course, you will be basically taught that there are three phases worth knowing, right? And the first is the metal, right? The second is the band insulator. The third is the BCS superconductor. And by now, typically when I have taught the courses, the time has run out, right? And I have not had time to introduce this phase, right? And this phase is the filled Landau level, right? So we basically, we have been taught that these are the four phases, and actually much of what we teach in standard courses is analyzing each one of these phases in some depth, and that's what we believe. And for a long time, this is what was the understanding, and in some sense, much of our work was trying to see whether known materials fit one of these paradigms, and if some of them showed some peculiarities, what are those peculiarities and so on. But things have changed in the last 10 to 15 years, and condensed matter people have learned two more words, right? The first one is topology, and the second one is entanglement, right? So what I'm going to talk about in my talk mostly is this idea of topology, And I will have some very brief remarks about entanglement. And actually, I thought I should also do something about entanglement, but I realized that that will go way too long. And actually, some of the things that Bhaskaran talked about this morning actually are very intimately connected to the notion of entanglement and so on. So for example, he talked about the toric code, and there is some very distinct feature in the entanglement structure in the toric code, which is different from the standard phases that I showed, right? So those are the aspects that I will not be discussing. Okay, so what will I be discussing? So what we now understand is that in phases which we call as short range entangled, in some sense very minimal entanglement, there is a complete understanding of the gapped phases of fermions. And that understanding is shown in this periodic table. And you can see that it has some labels here and some numbers there. And I'm not going to discuss what it is now, but I will elaborate on this as we go along. And this thing is called as the tenfold way because there are 10 rows here. Okay? And I'm going to be mostly talking to you about the tenfold way. Okay. All right. So the question first I want to do is, if you're not from the condensed matter background, I want to sort of motivate you why you would even expect something like this. Why are not all insulators the same? Why would you even think that there has to be different insulators, right? So that's what I'm going to do, and I'm going to do this in a very elementary way, starting from very basic quantum mechanics. Okay. So what and why of topology, right? Okay. So I need some very minimal quantum mechanics for this part of the talk, and that is, first is that the fermions are the ones, the kind of particles that I'm going to be discussing. So they obey Pauli's exclusion principle, so that is written in an equation here. And I have quantum mechanics, which means, I have states and operators and all that stuff. So I bring that into the game, okay? So what I will do is, I will construct the simplest possible models, which actually show you a metallic phase, an insulating phase, and then pose a question, is there only a single insulating phase? Right? So that's how we are going to build this story. Okay. So I'm going to use a notation here. So you see, when you were in 12th standard, you were asked to write down what is the structure of carbon atom, and we all wrote this down very happily. And I used to wonder, what exactly do you mean by putting an electron in a box, right? And so in fact, first time I saw particle in a box, this is what I thought they were meaning, that you draw an arrow in a box, right? Okay. But what actually this means is that it's a short form for writing a determinantal wave function, which actually includes the anti-symmetry of the wave function. So I'm going to use this notation, very efficient notation of the chemists, that such boxes actually are short forms for such slated determinants, right? Which actually encode the exchange anti-symmetry of the wave function, right? So that's the idea. So now if you ask the question, what are the distinct phases of electrons in a Coulomb potential? Of course, that's not a well-defined physics question because phase is typically an infinite number of degrees of freedom, but let's just be generous. So you see, if I have a Coulomb potential, right, and I start putting in electrons, the phases that you get is the periodic table, right? So that's crudely the idea, right? So you see, and we all know that there's the repetition of 8 and so on. And of course, that was, Mendeleev, of course, didn't see this piece, but he actually discovered this periodicity of 8. And magically, the table I showed you also has a periodicity of 8, right? So it's kind of Mendeleev all over again, right? But that periodic table, if you like, is for 10 to the 23 electrons, for an Avogadro number, for a large number of electrons. Okay, so this is what we are going to see. Okay, so let's start off. So what I'm going to do is, again, I'm going to assume that people haven't seen the tight binding model. Of course, anyone who has done any condensed matter course would have seen this. So I'm going to start with the simplest model of electrons in a one-dimensional system. And this is called the tight binding model. So the idea is that, so if you want a concrete picture, you can imagine that there is a chain of protons here, and each one of them have this 1s orbital around them. And so the idea is that if I put an electron in the 1s orbital, it can hop to the neighboring site by an amplitude t and so on, right? So now you see that the way I've constructed this, the system has some translational symmetry. So momentum is a good quantum number, but we are in a crystal, so not all value of momenta are allowed, or not all value of momenta are meaningful. right? Because, if you take k and k plus 2 pi in a system where the lattice spacing is a single unit, then you will see that it will come back to itself. So the set of allowed momenta actually go from minus pi to pi, where minus pi and pi are identified. So in the sense, if I have a crystal, the space of momenta actually becomes a circle, right? That's what I've shown here. And then for every given momenta, there is an energy eigenstate, which we can solve for this problem fairly straightforward by going to the momentum space, and this is the dispersion, okay? So in d dimensions, you can see that the space of momenta actually become a d-dimensional torus, right? That's the Brillouin zone, as it's called for the d-dimensional system. Okay, very nice. So I started off with this, and I have this because I start off with an n-side chain with periodic boundary conditions. So I have these momenta which have labeled by empty squares, and remember I'm going to use the chemist notation to find the ground state now, ground state wave function. So I need to pick out the ground state. So what do? I want to have a filling of electrons which is n by 2, which is half the number of sites. So what I have to do is I have to pick out n by 2 lowest energy single particle states and make a wave function of the many electron system by quote unquote filling them. Filling means that I take all these states and construct a slated determinant out of them, and this is exactly where I'm borrowing the chemist notation. So instead of the arrow, I'm just coloring them, right? Because I'm also having spinless electrons here. So this is the ground state, okay? All right. So this ground state is called the filled Fermi C, right? And as I just said, these filled pigeonholes actually make the slated determinant ground state wave function. Okay, now it won't take me long to convince you that this is actually a liquid state. And that's easy to see because I ask, what is the first excited state of the system? And how much energy does it cost me to excite this, right? So if you look at what is the first excited state of the system, and we're going to take n very large, you will see what I can do is I can construct a state orthogonal to the ground state, a new slated determinant where I leave this pigeonhole empty, but I occupy the next pigeonhole. So I have a little bit of higher energy, and that the energy difference is the energy of this state minus the energy of this state minus the energy of this state. So if you look at this a little bit longer, you will see that excitation energy is actually proportional to this delta k, which you remember. So that's the slope of this dispersion times delta k. But delta k, remember, goes as 2 pi by n. So in the thermodynamic limit, it costs me no energy to excite, right? Which means if I apply a very, very small electric field, I could have matrix elements, and there's no energy for excitation, so you can start flowing a current. So this is roughly saying that this doesn't have any shear modulus in quotes, right? It's one dimension, of course, there's no meaning for shear modulus, but it doesn't resist the electric field. So that's the idea. So this is the liquid state in one dimension, if you like. Okay, so now if you stop here, you will be very puzzled, because how can I have an insulator now? Right, because so in this world, if I believe that this is the all possible state of electrons, I cannot have an insulator. So to get an insulator, I have to do something. So one thing you can immediately do is, I can take, instead of n by 2 electrons, I can take n electrons, which means there's a unique state for the full system. So the Hilbert space of this n particle, n fermion system on these n sites will be a single state, so that's kind of boring because then nothing happens, right? So you have to do some more work to discover why there are insulators. So in fact, if you think about classical physics, you will see that the existence of insulators itself is a puzzle, right? So, if you believe that, ions can donate electrons to crystals and so on, then you will be wondering, why are there insulators, right? So for that, you have to do something more. And that something is the following. So let's look at a real insulator like sodium chloride, pure sodium chloride with no defects and so on, no defects, impurities, nothing. That's a very good insulator. So what happens there is, you see, I have to put in some more physics into this. So what I'm going to say is that I have a chain, but not every ion on the chain is the same, right? So there is a difference in electronegativity. This is a word that I learned from chemists and I use it without knowing exactly what it is, right? Okay, and how I take the difference in electronegativity is that I say that, oh, if the blue is a chlorine, then there is some gain in the electron sitting there, gain in energy in the electron sitting there. And I sort of look at this symmetrically, so I say that if it is in the sodium, it costs a little bit more energy, and if it is chlorine, it costs a little less energy, okay? So now if I go and solve this problem, right, I will see that I will get two bands, not a single band, and you can see that very straightforwardly why you should get two bands, because every unit cell has now, quote unquote, 2 degrees of freedom. So when you go to the momentum space, you will see that everything has 2 orbitals and you will get 2 bands, right? So you get these 2 bands. So now you see I have 2 rows of pigeonholes, one for the lower band and one for the upper band. Now again I put n by 2 electrons, and now you see I have my ground state is these set of states filled, and this is my ground state, right? But now note that if I try to create an excitation in this, right? If I try to create an excitation in this, the excitation energy is, what do? I dock off this electron from this so-called valence band, and I occupy the state, I construct a slated determinant with this state instead of the state in the valence band, and that's the state I will have. And you see this will cost me a finite energy for excitation, which you can actually show is actually roughly proportional to E0. You can actually show that from explicit calculation, right? So you will see that excitation energy is actually independent of the system size and is finite even in the thermodynamic limit. And therefore, if I apply a small enough electric field, whose strength is in some energy scale which is much small compared to this E0, the system will simply ignore that. It will just rearrange its states in an ever so slightly different way, and it just ignores it. It becomes a dielectric. It may get a small dipole moment of some kind, and there's no current that's going to flow. So this is the solid phase of electrons. Okay, so this is the idea. Okay, so now the question that comes up is this the only possible solid phase or insulating phase of electrons? Okay, so this is the question. So I hope in the next 5 or 10 minutes, I will convince you that there are other insulating phases which have something different from the one that I showed you, but cannot be distinguished by symmetry. And that's what I want to show you. Okay, there are distinct phases which are not distinguished by symmetry. Okay, so for this, I'm going to introduce something called the SSH model. Sumati will discuss a closely related model called you're going to discuss the Kitaev single, this one also, right? So she will discuss in some depth. I will just briefly touch upon this and tell you what's going on here, right? Okay, so what I'm going to do is, I'm going to have all the molecules or atoms the same. But what I'm going to do is, I'm going to arrange them in such a way that the electrons can hop with a different amplitude between A and B in one unit cell, and from B to A going to the next unit cell has a different amplitude. So if you're familiar with something called Peierls distortion in crystals, I'm roughly Peierls distorted the single chain. That's what I've done. Okay? Now if you look at the band structure, you again see that the dispersion looks exactly the same, right? Qualitatively it looks exactly like the sodium chloride case, and there is a gap, and that gap is T2 minus T1, which is the difference of these hoppings. Okay, and again the ground state is filled slated determinant of the valence band state, and so apparently looks no different from what I showed before. So what would happen? So it turns out that you cannot see any difference unless you do something drastic. So remember, I had this chain and I had put periodic boundary conditions. So now I take a scissor and just cut the chain. So what have I done? I have a system with finite system with open boundaries. And then something magical happens, right? So what I've shown here is that I'm looking at T2 by T1 is 0.5. And you see, this is the spectrum of the chain. So I've just numerically solved this. And what I'm showing you is some some number, so it's a chain which is 100 the unit cells long, so there are 200 eigenstates. So you see that there are all these eigenstates and there's no energies between this value and this value, which means that there's a gap and therefore there are no energies, and then these are the states in the valence band. So now what I do is I look at T2 by T1 greater than 1, right? And you see, oh, it looks exactly the same. But hey, you see, this is not a bug, it's a feature, right? You see, you just get these two little dots here, which are two eigenstates, almost exactly at 0, right? So when T2 by T1 is less than 1, you have no states in the gap. When T2 by T1 is greater than 1, you see that you pick up two states in the gap. So now, if you just count, you see that, oh, having this states in the gap or not having the states in the gap is a yes or no question, right? At that qualitative level, you can see that these two objects are different because one says yes for a yes or no question and the other says no for a yes or no question. Okay, that's a great question. So there is no symmetry difference between T1 and T2, but the way we will play this game is, we will label our unit cell in a certain way, and then we will define Hamiltonians in a certain way. So in the process of doing everything, the labeling of states we will never change. We will change the interactions between them. We will change the Hamiltonian, but we will not change the labels. We will not go and we will not relabel the unit cell and so on, right? So what appears, so what that will do, if you do that, what you would call a trivial state and what I would call a topological state will differ, right? But both of us will have distinct states if you decide to call some different convention. Distinct phases if I have different convention. Yeah, I have to be careful where I cut, right? So in this way I have set it, in the way I have set it up, the left side will be the A sublattice and the right side will be the B sublattice. No, the gap in this case I am varying by tuning some parameter in the Hamiltonian, which is the ratio of T2 by T1. And the gap, the physical magnitude of the gap is difference of the T2 and T1. In this model, it is built in that way. So yes.
You can vary the level of metallicity.
But no, let's first discuss the clean system. Let's not bring disorder and so on, right? And we'll come to the issues of disorder and all later, right? So, by the way, this is a serious problem in people who do, you know this much better than I do, right? People who do experiments with topological insulators, because if it's not clean, then actually it spoils everything. Yeah, that's there, that's an issue. But let's just first discuss the clean system. Okay, so this is what happens. Okay, now what I'm going to do is I'm going to take a look at what is the wave function corresponding to this particular energy. And what you find magically is that those wave functions, now this, what I'm plotting on the x-axis here, is the position along the physical chain in real space. And what is being plotted here is the probability of finding the electron if it has that energy corresponding to that zero energy, right? And you see that there is a wave function localized on the edge. So what am I showing you? I'm showing you that if I am in the situation where T2 by T1 is greater than 1, if I cut a finite chain in an appropriate way and make a finite chain out of it, then you will see that it has an edge state. Edge state where in a regime of energy which is forbidden by band theory. Right? Yes.
It seems that the probability at the B side seems
0. Yes. Yeah, that's a great question. So you should worry about, how can the electron hop if it's not allowed to be there? Welcome to wave mechanics, my friend. Right? So interference, right? So you can view this as interference of e to the I kx plus minus e to the I kx. So on the odd sides you can, so this is the beauty of wave mechanics. Right? Okay. All right. So this is the story. Okay. So now qualitatively we see that something when T2 by T1 is greater than 1 is different from T2 by T1 less than 1. Okay, now Subhro, I'll just answer your question. So you can show by a little bit more work that even if you put some disorder in this statement that for a certain parameter range of T2 by T1 greater than 1 or less than 1, this feature of having an end state is not changed. Okay, so I have hopefully demonstrated to you there are two distinct phases, and if you want some way to characterize the phases, ask the question that if I put this on a finite system, does it have end states or not? Okay, if the answer is yes, you will say it's a topological phase. For you don't know why you are calling it topological, but you will call it a topological phase. And if the answer is no, you would call it a trivial phase. Okay, so in this picture, what I have shown you is the following: that when T2 by T1 less than 1, this is all trivial, no end states, and T2 by T1 greater than 1, you call it topological, right? Now, another point, suppose I had a way of tuning T2 by T1. So in condensed matter, this may be difficult, right? You may have to do something like applying pressure or doing something. But in cold atoms, you know, which is the solution for all problems of humanity, you can do anything in cold atoms, or so I am told, right? You can actually set up systems fairly easily, much more easily than condensed matter, I would say, you know, to try and see whether you can actually tune these things. So here's what I'm going to do. I'm going to start with T2 by T1 less than 1. So I'm looking at the spectrum of a chain, and you see I'm sort of changing it. See, it's so easy to you know, do tuning experiments as a theorist. All you have to do is to just click this, right? Okay, so you're going, you see the gap is closing because the magnitude of the gap is T2 more of T2 minus T1. And when T2 equal to T1, that's a phase that you're familiar with, that's our liquid phase, right? When T2 is equal to T1, this is just the same old metal that we saw. Right, so the gap closes, so it's gapless at that point when T2 and T1 are equal, and then it reopens again, but now you see there's the end state, right? So what I just showed you is a quantum phase transition, quantum because I'm looking at the zero temperature, I'm looking at how the ground state is evolving, and I'm tuning a parameter T2 by T1. So whatever change is happening is because of the laws of quantum mechanics, not because of some thermal fluctuations or anything, right? And therefore quantum phase transition. And you see, I go from a gapped system for T2 by T1, which doesn't have end states, to gapped system for T2 by T1 greater than 1, which has end states, but the point where the change takes place, it's gapless, right? And it also satisfies all properties that you would require of a critical phase that you would see in statistical mechanics, which is, you know, which is gapless and so on. So that's the connection to quantum phase, the phase transition part of it. Right? Okay. So that's the story. So now you ask, why are you calling this topological? Where is the topology? Right? Why would I want to call this a topological phase? Okay. So that's the question that I'll attempt to answer in the next slide. Okay. So now if you do a little bit work, you will see that the wave function, the block state corresponding to this valence band, sorry, I have to go back. Oh, no, I actually already had that there. Sorry, I actually had that there. Let me show you. So you see, these are the two, this is the valence band and this is the conduction band. So let's just go to a particular K, and you look at the wave function of the block wave function of the valence band state. So you can show modulo some uninteresting things. You will see that there is a ratio of phases between what is there on the A sublattice and what is there on the B sublattice. Please note that this is not the overall phase of the wave function. Please note that. This is the relative phase between what is there on the A sublattice and what is there on the B sublattice. Right? So now you see that the valence band wave function can be characterized by a single phase. What is the single phase? It's the relative phase of the wave function on the A sublattice and B sublattice. So you see, now if I were to think of this as if I were to think of the Brillouin zone as which is a good place to write? So group photo everybody knows, right? Okay, maybe more interesting is the coffee break, but okay, yeah, all right. So fine. So what you can do is the following, right? So imagine that this is the Brillouin zone. So we start from minus pi and go to plus pi. So what am I attaching to the points in the Brillouin zone? I am attaching a phase, which is the e to the I theta of k, right? So now imagine, just imagine that I attach a phase. So this is like, you should imagine that I'm putting something on the dial of a clock. So you see, if I'm going to attach this phase, there are distinct ways of attaching phase going from minus pi to pi. And remember that minus pi and pi are identical. So whatever you're attaching here, you must attach the same thing here. So what can happen? So you see, you could attach in such a way that the clock, the hand on the clock doesn't do a full revolution of the clock. What you can do is you can sort of go this way and come back, right? Which in this language, if I go along k, you will be doing a loop here. You will not cross the origin. You see? All right. You could do something else. You could start like this, and then you could actually go, I'm drawing the tip of the thing. It could sort of go around like this and do a loop and come back, right? It does a loop, it goes around the clock. And so if you think of it like a belt, in one case the belt doesn't twist, in the other case the belt does a twist of 2 pi. And therefore, the slated determinant wave function of the gapped phase for T2 by T1 does not have this twist, whereas the slated determinant for T2 by T1 greater than 1 encodes this twist. And you see, whether it is twisted or not cannot be smoothly connected to each other, because you have to have a twist or no twist. And the way you can do this, how can you go from one to the other? You have to cut something. So it's like opening a lock, right? So lock is the daily, our padlock is the daily place where we use topology, right? So you go to the trivial phase, you open the key, right? And you have to go to the trivial phase. And then if you want to lock, you have to do the phase transition using the key. And the point of phase transition here is this place where it becomes gapless. And then if you think about it a little bit, you will realize that the phase is ill-defined there. Why is the phase ill-defined? Because just at the phase transition point, you will see that this point will touch the origin, which means in some sense that I had this hand on the clock, right? The hand will not be on the clock, it will actually come and touch, it will become 0 length object. So that's like cutting, right? So this is where the topology is encoded, and this is what is topological about this. Okay, so now the answer coming to the point about disorder. So now you see, if I take this system, there's a slated determinant, so there's a twist encoded. Now suppose I put some ever so slight amount of disorder, it breaks translational symmetry. Yes, sure. However, you can just intuitively see that the wave functions, if you do some kind of perturbation theory, will change a little bit. But you see, in some crude sense, you see that this twist cannot be destroyed. So it's robust. What that means is there is a regime in the space of Hamiltonians, right, in which this twist will be the same. So all those ground states are actually physically the same universality class, if you like. Yeah, actually Professor Berry did the work many years back, right? So visualization is by, you can see, what is the Berry phase. You can write, so I'll just tell you. So what you can do is, I wrote something here, no? So you can think of something like this. In this case, and integrate this from minus pi to pi, and you can show that this is an integer. And the question is whether this, okay, I'm being slightly sloppy here. So if you want, I can do it like this. Right? So if you do this on a two-dimensional system, that object will become like Chern number, and you can show that is like the Berry phase that gets picked. Yeah. You can visualize it that way. Yeah. Okay. So there are many other experts, and if there is a better answer, I think other people are also welcome to comment. Okay, how am I doing with time? I'm halfway through, is it? So 26 by 72 is less than half, right? So that means that, Google, this thing will say recalculating. So I have to recalculate now. Okay. Okay, so I'm done with the first part of my presentation, which is giving you a flavor of where this comes from. Yeah.
At this level, the fact that cutting.
In the other phase, what will happen is that this angle will not twist. So it will become like, okay, maybe I have a piece of paper, then I can show you. So it won't twist. It can deform, but it will come back to itself. So if I stretch that, okay, yeah. No, I can remove my belt, but that may offend the modesty of several people, right? I hope I won't be frisked. Okay, all right. So what will happen is, so in the trivial phase, Rajaman, can you just indulge me? You can just hold this. Yeah, thank you. So in the trivial phase, what would happen? It would do something like this, but you see, if I stretch this, it's equivalent to having straight one, right? But in the topological one, I will go by this, and then I will. No, but I made that point clear, right? But when you do it, you're going to cut unit cells. You will not break a unit cell. That's exactly what so you have to respect the unit cell throughout. Yeah. So otherwise what will happen is you get, say, like dangling bonds and all that. So then there's other stuff that comes in. It becomes gapless. Okay, all right, okay. Now you're asking a slightly more technical question. So let me just go back to this. Okay, so this picture is loaded actually, right? Where's the person who was? Yeah, okay. So you see, this distance in this picture is the energy of the valence band. The magnitude of that's the energy of the valence band. So if I am in the metallic phase, when T2 equal to T1, this point will become the dash point is exactly that, and you see this point becomes zero energy. And at that point, the phase is not well defined anymore. It becomes zero. So it's like cutting. Right. So if you want to think, you are tearing the paper. Yeah, so in the thermodynamic, yeah, that could be. Yeah, because it depends on, you choose odd, even, and so on. But in the thermodynamic limit, it will be exactly zero. Yes. Yeah. So, given the Hamiltonian, you can compute the winding. Yes. Given the Hamiltonian and you have labeled the motif. Symmetry. No. You will see. So it will become, that labeling will become a representation of symmetry. I will show you. Computation of the phase requires to say what the symmetries are. But it requires, no, agreed. I agree with you. But I'm saying that in choosing e to the I theta k, I have to, so I say that the top thing is always A and the bottom thing is always B. And throughout this tuning of the Hamiltonian, I have to hold on to that. If I change that, then there is no, actually, you lose the control on the stuff. You can't start relabeling in the middle. Saying that it seems like the formula is blind to what we call A and what we call B. No, it is not blind to that. It's not blind to that, because if I call what I call A and B, you can see that I can change stuff. So if you were to change the labeling, would that become trivial? Yeah. So what will happen is, if I were to change the labeling, so you can see that's why I first wrote psi and I changed it. So you see, if you take the simple winding number, you can actually get any integer you want, because you can add overall phases to this. So suppose I would write the block state. Now this is block spinner, not the e to the I theta, the full one. Then I can get any integer I want, because what will I do? I will simply just take and hit e to the I theta in such a way that it just winds around, right? So that is not, just taking this is not it's not invariant to that. Okay. So can I fast forward to some slide that I'll show later? So this is where the notion of symmetric spaces will show up very, very quickly, because that will answer the. So where this choice will come up is very important, and it's an extremely important point, but okay, I'm just, so you see, so once you decide what is your A and B, the true wave function, irrespective of all gauge freedom that's allowed, will become some object like this, where what you put here and what you put here, what you're quotienting out, will be determined by what you call A and what you call B. Okay, I'll come to this again. So maybe it's a slightly technical answer, but okay. Again, other experts are, actually experts are welcome to say, right, okay. All right. So now I showed you in one dimension, in some context, that there are two phases, right? So now you can say, why are there only two? Why not more? So you could say, oh, you have showed me only one edge state. I could construct something with two edge states. So maybe there is other phases. So then the question is natural. What are all the phases of gapped electrons? And here's the answer, right? So this answer was discovered about 10 years back. And what is shown here on the x-axis, on the y-axis, are some labels A, A3 and so on. And here is where these are some symmetries of the fermionic system. And what is shown on the x-axis there is the spatial dimension, right? And you see there's an entry associated with a symmetry label, say class D, and if I look at one dimension, you see that it is Z, right? That means that there are integer infinity of distinct gapped phases, each, if you like, labeled by an integer. If it is Z2, there are two distinct phases. If it is 0, there is only one phase. Okay? So what I am going to tell you in the next half hour or so is what are these labels and how you can sort of see that this is actually a plausible thing. So where is this periodic table story coming from? So here's the remarkably beautiful stuff. So, so this is 0 dimensions, and this is 8 dimensions, and you see that the table in the 0 dimensions is exactly same as the table in 8 dimensions. So there is a periodicity, 8-fold periodicity in spatial dimension, right? So actually if you read Professor Mukunda's book, you'll actually realize where this periodicity comes from, because he has this beautiful discussion of Clifford algebras and Lie groups and so on, so it's actually related to that. Yes. I will come to all this. Yeah. So I will show you that, so all this geometry of symmetric spaces, nature had to realize it's in some place. So it found fermions, right? So that's the way to put it. So you will see that, I will discuss all this in some depth now. Okay. So this is called a tenfold wave because there are 10 classes, and this is the symmetry, this is the set of insulating phases of systems in different dimensions for each symmetry class. And this is now called as a tenfold wave. Okay? All right. So this is what I'm going to discuss now. So very quick summary of what I'm going to do. So I will show you that in addition to the usual symmetries that we look at, like translation, rotation, and so on, if you are fermionic, it's very important to be fermionic in the way that I'm going to discuss this. You will see that there are other kind of symmetries which are intrinsic to being fermionic. Symmetry operations, let's say. Whether something has a symmetry or not will decide what kind of class it is in. And based on this, you will see that there are 10 symmetry classes, right? And these 10 symmetry classes are just the 10 symmetric families of Cartan symmetric spaces. And what I will try to show you is where are these non-ordinary symmetries like time reversal and charge conjugation sublattice, where they come from, right? Why are there 10 classes? I will just very briefly discuss what is the connection to geometry, etc. And then the question comes, how does these distinct topological phases arise once you know that there are these symmetric classes, and if I give a spatial dimension and a particular symmetry class, how can you decide whether there is a topological phase? So that's what I'm going to discuss. Yeah. Yes.
Is there a molecular?
Please wait. Please, I will come to that, right? Yeah. Okay. All right. So what I'm going to do is I'm going to start with some very elementary considerations and probably to set the notation a little bit. Okay. So I start with a system which has L orbitals, and let's just take them as orthonormal, right? L orbitals. And what I'm going to do is I'm going to talk about fermions, right? And I'm going to create fermions starting from vacuum. So if I create a fermion, I create an electron or a fermion in this orbital I. So I would just call it that. And of course, these fermions satisfy this, this anti-commutation algebra. Now you see, I can discuss sectors of the Folk space or Hilbert space where I have NP fermions. And you can see that they are actually created by these set of states. And the dimension of the NP dimensional subspace is, or the NP particle sector if you like, is L choose NP. So what happens is, the Hilbert Folk space actually looks something like this, right? So this is the vacuum, this is the single particle sector, this is the NP particle sector, and L minus NP particle sector, L minus 1, and all the way to L particle sector, right? So mathematicians have a very nice way of saying these kind of vector spaces. They say they are graded. So this is a vector space which is graded. Now this becomes important, right? So this is a graded vector space, graded by particle number, right? Okay. So usually, we discuss general Hamiltonians, but here I'm going to start with some non-interacting Hamiltonians to begin with. And the starting point is to note that if I take a non-interacting Hamiltonian and ask what are all the set of Hamiltonians I can write down, you see that the space of Hamiltonians will be a real vector space, because a Hamiltonian plus another Hamiltonian cannot be, you can't linearly combine with complex numbers because you will lose hermiticity general, okay? But you can combine it with real numbers, so it's a real vector space. But if you think about this a little further, you'll realize that it's more than a vector space, it's actually a Lie algebra. I am always finite dimensional. You have probably already noticed that. Yeah. Right? So there's L and everything is finite, right? We don't. So you are worrying about quantum field theory and so on. So we will come to that, right? Okay. Okay. So that is the story. Okay. And what you will see is that because of this, I'm just motivating it very crudely, right? So you can see that this is the time evolution operator. So you see that some Lie algebra structure has to be there, and in fact, you can show that the space of Hamiltonian is exactly isomorphic to the Lie algebra of the unitary group of L orbitals. Okay. All right. So now what I'm going to do is I'm going to discuss the notion of symmetries. So the first notion I need is the notion of a symmetry operation. So symmetry operation is some kind of transformation or a map from the Hilbert space to itself, which leaves the magnitude of inner product of any two vectors unchanged, right? So that's the statement. Now Wigner proved this very important theorem, right, which says that every symmetry operation is either a linear operator or an antilinear operator, and this is an extremely beautiful result, right? Okay. And then the set of all symmetry operations will form a group, which I call GO, set of all symmetry operations. A symmetry operation is a symmetry if it leaves the Hamiltonian invariant. Okay, all right. And the set of all symmetries will form a group which is a subgroup of the set of all possible symmetry operations, right? And this group is simply called G. Okay, so typical symmetries and symmetry operations that we have are translation, rotation, and so on, right? This is what we have. Okay, so now you see, if you're fermionic, you realize that you can actually sort of expand this notion of symmetry and ask for maps which preserve inner product and the grade of the vector space. So grade preserving isomorphisms, if you like, right? And then you see that there are grade preserving isomorphisms which take you from the same particle sector to itself, or you notice that L choose NP is same as L choose L minus NP, which means I can have these kind of symmetry operations which are transposing. So they change particles to holes in condensed matter language and vice versa. Right? So you can have this or that, and now each of these can be linear or antilinear. Right? So you see that there are 4 distinct types of symmetry operations. Right? And in the first case, what happens is, if I were to write the usual kind of operation which maps the particles to particles, then you see a creation operator will go to a creation operator times some matrix, unitary matrix if you like. However, if I were to do this transposing operation, a creation operator will go to an annihilation operator because I have to map particles to holes with a unitary. Right? Okay. So these are the 4 operations, and so symmetry operations for fermionic systems, the usual ones and the transposing ones, and the linear usual ones is what we call as the ordinary symmetries, like translation, rotation, and all of that stuff. Right? And these other operations, which I call as non-ordinary for lack of vocabulary or whatever, or imagination maybe, right? Okay, so this is the antilinear usual operation, and the transposing linear operation and transposing antilinear operation. So you get this, right? And the central idea for classifying intrinsic symmetries of fermionic systems are these non-ordinary symmetries. Okay, all right. So now I'll show you some nice properties of non-ordinary symmetries. Suppose I have 2 non-ordinary symmetries, distinct non-ordinary symmetries. If I multiply them, I will get a non-ordinary symmetry which is the other kind, the third kind. Right? So this is what I've shown here. 2 of the same kind will become an ordinary symmetry. 2 of distinct kind will become the other kind. So you see secretly there is a group hiding under this. So if you take this group, there's a normal subgroup of the usual symmetries, you quotient it out, and what you get is the, what you get is, let me quickly show you, is the Klein group. You actually get the Klein group as the basic group, right? So let me go through some elementary discussion before that. Okay, so you get this kind of structure in which if I have 2 distinct non-ordinary symmetries and multiply them, I will get the third kind, and so on. Okay, so now if you go through this, I start looking at fermionic systems which do not have any ordinary symmetry. So you can make this more formal by looking at some representation of the ordinary symmetry and then working with that representation and so on. So it's like, it's all identity, all the ordinary symmetries are identity, right? Okay, so what you will see is that there is at most, if I have such systems, there is at most one kind of non-ordinary symmetry. So if I have say transposing linear symmetry, there can be only one of those kind if I don't have any other ordinary symmetries, right? And then, so you can call this, so the usual antilinear symmetries, you can give it familiar names. So you can call this time reversal, you can call this charge conjugation, you can call this sublattice. The high energy people call the sublattice chiral, but okay, we will call it sublattice, okay? And so this is what such systems which don't have any ordinary symmetries is what I call grotesque, because in some sense if I don't have ordinary symmetries, it doesn't look nice, right? Okay, so now you see, there are only 3 possibilities. Either there are no ordinary symmetries, no non-ordinary symmetries. Type 1, there is only one non-ordinary symmetry, and type 3, there is no type 2, which has all 3 non-ordinary symmetries. Because if I have 2 of them, the third one will come automatically because the product is the other one, right? Now based on this, you can do some very interesting things. You can show that time reversal square will turn out to be either +1 or -1. So the fermionic system has to choose that it becomes +1 or -1. Okay, and a proof of that is sketched there. I won't go through this in detail here, but I will introduce this idea again one more time later. Okay, so now you see, by taking into account all possible t square is plus 1 minus 1, similarly c square is plus 1 minus 1, but s square will always be 1, you will realize that the intrinsic symmetries can be realized in the following way, right? Type 0, no intrinsic symmetry, that means this is time reversal 0, charge conjugation 0, sublattice 0, no intrinsic symmetries. So this is called as class A. Then you could have type 1, in which there is one non-ordinary symmetry. So I can have A1 where this is plus 1, that means t square is plus 1, and then t square is minus 1, A2, and then c square, the charge conjugation, that is plus 1 minus 1, and A3 where there is only sublattice symmetry, right? And these classes where all three symmetries are present, and you see this is plus 1, and all other combinations. So this is where the 10 classes come from. Okay, this is an elementary way of doing it without the mathematical baggage. Okay, now let me bring some ideas, and this is also related to our question about phases and so on, right? Yeah. Okay. Okay, all right. Okay, so you see that I showed you the periodicity of 8. So you can actually get the periodicity of 8 by following these arrows. Okay, so if I use the word Bott periodicity, it will not make, yeah, okay. So the arrows actually represent that, okay. So in some sense, anything in this class will also, have, you can build from other classes and so on. And if you follow this arrow and go here and so on, then you can, that you can traverse that periodic table as well. Okay, so now what this allows us to do is you can find canonical. Remember when I did the transformations, the psi went to some psi dagger times u. There is some way to find some canonical representations of these things, right? And that's what is done here. And I just want to show you some things that you will be familiar with. So if you take class A2, you will see that class A2 can be represented only in a space which is even dimensional. It's forced on you. And Sumati will talk more about this. This is called, this will bring you the Kramer's degeneracy, right? Class A2 is the one where t square is minus 1, right? The time reversal square will become minus 1. And you will see that that can be done only in a space which is two-dimensional, right? You can't have it, so it will all pop out of this calculation, right? So you will see that there are all these natural representation symmetries, and what this allows us to do is it allows us to find the spaces of Hamiltonians in which these symmetries can be implemented. Once you have these representations, then you can find what are the vector spaces and all the Lie algebras or quotient spaces that will hold these symmetry classes, right? Okay. So now let me tell you my main story about where the phase determines the phase. So there is a much more beautiful way of looking at and understanding this. This is from representation theory. So what you realize is that the abstract group of symmetry operations of fermionic systems, if you quotient out the normal subgroup of these usual linear operations, is actually the Klein group. And the Klein group is what I'm showing you here, right? So it has these operations, the identity, time reversal, charge conjugation, and sublattice. And it has all the structure as I told you. If I take two of the same, it will give me identity. If I take one with this, I'll get the other one, right? This is the Klein group, Z2 cross Z2. That's the Klein group. And the claim is the following. If I have type 0, the symmetry, the physical symmetry that the system is actually the identity subgroup of the Klein group. If it is type 1, it's one of the Z2 subgroups, which is either the time reversal, the charge conjugation, or the sublattice. If it is type 3, it's the full Klein group, right? But then you will say, hey, there should be only 1, 2, 3, 4, 5 classes. Why are there 10 classes? That is where the idea of phases come in. Because in quantum mechanics, representations need not be linear representations. They can be projective representations, right? What do I mean by projective representation? Okay, so suppose, okay, no, I will show it to you in the next. I think it's there in the transparency. Okay, okay, all right. So projective representation is the following. So for a representation, I have a group, an abstract group, which I believe encodes my symmetry. And then I have some vector space on which I'm going to have operators, and I'm going to map the group elements to the operators on the vector space. So suppose I have an abstract group G, and I say that there is a DG operator which represents it, then typically I would want DG1, DG2 is equal to D of G1, G2. But in quantum mechanics, I don't need this, right? I don't need this because I can multiply any state by a phase. So if you read some of Professor Mukunda's writing and so on, he calls it the ray space. So you only worry about the ray. You actually don't, so I'm doing this by what I'm doing here is that I'm taking the some unit vector and multiplying by e to the I theta. That's what I'm doing this, right? So you only care about the direction in the Hilbert space. You don't care about what is the phase. Okay. All right. Yeah, I mean, okay, this is fantastic to have you in the audience. Yeah, okay. All right. Okay. So now this object is called a, so if I were to get in some phase like this is what we call as a Schur multiplier, because of course Schur postulated this. Okay. All right. Now there is a condition on this. The condition is the following, right? If I were to try to see the the associativity of group, then it imposes certain conditions on me. So what actually happens is, if I were to do this, D of G1, G2, G3, somehow the physics should be determined by D of G1, G2, G3, all of it together, right? So that means the phases will come in certain ways. So what I have to do is, I have to define a notion of how a group element will act on the phase. So that's what is this notation telling you. What is the action of a group element on the phase? This omega of G1, right? In the cases of our interest, because we are interested in fermionic systems, I may not have time to tell you. So this action actually is either just identity or conjugation, right? So that's what happens. So now the question is, if this is what I want and I give you a certain group, what are all possible distinct Schur multiplier systems? Okay, now there's a beautiful theorem you can show that the Schur multiplier systems, the distinct ones, themselves form a group. Right? The Schur multiplier systems themselves form a group. And that group is called the second cohomology group of the group G. So the math problem is reduced to computing just cohomologies of the groups, of the Klein group and its subgroups. I'm sorry? So this comment was made to me by some mathematicians in TIFR. I thought they were being their usual selves. But okay, so obviously the way the book I read it from actually has this notation, right? Yeah. Yes, but I've heard this comment before. But I didn't change it because I went back and looked at the book, and even the TIFR people couldn't change the printed version. Right. So, okay. All right. So this is the idea. Okay. And now you can do the computation, and you can actually show that the Klein group and its subgroup has exactly 10 distinct representations. And those 10 distinct representations are the 10 symmetry classes. Right. So now you see this thing actually puts the whole game in a much broader framework. So if you go and read Weinberg's book on quantum field theory, so he will make this point that all particle content is actually representations of the Poincare group. So now you see that fermions are actually representations of the Klein group, right? So they had to be there because Klein group is so beautiful. Something had to realize this, right? So and this is what is the point. Okay, and based on this, you can actually get all of that information. The ones that I showed you, using this multiplier systems, etc. You can actually get back all this canonical representations and so on. Okay, so now I'm ready to discuss a little bit about what is the space of Hamiltonians which represents these symmetries. Okay, so what I'm showing you here is class A, which means there is no symmetry. There are L orbitals So what are the space of allowed Hamiltonians? It's the set of all L by L Hermitian matrices. So that's what this is. Okay, so now you see it generates, it's the generator of U1, of UL. So one symmetric space has been ticked off. Right? So now you go to A1, you will see that the space of Hamiltonians are ones you can find a representation with, they are always real. The whole Hamiltonian is real because T square is +1, it's always real. Okay, and now you see that is some quotient space. Okay, and if you exponentiate that, you will see that there's another symmetric space which is UL by OL. Right? And you can keep doing this and you will see all the symmetric spaces simply appear for different symmetric classes. So now you see nature had to realize, symmetric space is so beautiful. So nature had to find some system to realize this, and those are fermions. Right? And that's the point I would like to make. Okay, and this is the connection to geometry, and these are the 10 symmetry classes and so on. Okay, so now you can ask, oh, you are talking only about non-interacting systems. What is the story with interactions? So okay, so there are young people like Adip who worried about this and solved this problem, and they made bigger tables and chairs and so on. Right, and they are there in our paper, you can go and look at it. Okay, all right. So now comes the question, how do I get topology? So here I would like to appeal to the point that I just made, which is that if I'm in class A1, yes, the Hamiltonian is real, which means the wave function can always be chosen to be real. There's a basis in which the wave function is real, which means that if you're not choosing it real, that means you're doing some gauge, which means that can be removed, definitely. So you see, what I'm trying to point out to you is that depending on what the symmetry class is, it will determine what kind of object you have for the wave function. So if I were to attach real numbers to this, you will see that I'll have no topology, because if I were to attach real numbers and I have to be smooth, so the only thing I attach is ones everywhere. So that cannot give you any topology. But if I were to allow to have complex numbers as wave functions, then you see I can get a twist. So now you can see how symmetry can bring in topology. Okay, I'm motivating this idea. Okay, yes, 10 minutes, yeah. Okay, so Adip, the advertisement will not take place. All right, okay. So now what I'm going to do is I'm going to go from so what I'm doing is I'm taking a GFS and I'm attaching a GFS to every lattice site. So now you see I have labeled, the GFS is the one which doesn't have locally any extraordinary symmetry. So now I have decided that A, B, C, D, whatever I have are the things which I call A, B, C, D. That's it. And it's in that basis that the representations are what I wrote down. Grotesque fermionic system. Right. Okay. All right. And then I now put this and I put this Hamiltonian. I choose this Hamiltonian so that it has all these symmetries. So I get a lattice model like this. Right. So you can go to quantum field theory by making this L larger and larger and larger and larger in infinite dimension. Right. Okay. That's the crude answer to your point. Yeah. Okay. So now I diagonalize this. Right. When I diagonalize this, I will get some set of occupied states and unoccupied states. Right. And what I'm going to do is I'm going to fill the occupied states and I'm going to have a gap. I'm going to discuss only gapped Hamiltonians. And I'm going to say two Hamiltonians in the space of Hamiltonians that I have are in the same class if I can find a path in the space of Hamiltonians to go from point A to point B without closing this gap. They are topologically equivalent. A notion of homotopy has just been introduced. Right? So I can go from, so there's a space of Hamiltonians, it implements some, so it could be one point in one of the vector spaces I showed you, right? I go from here to there and I ask, can I go from any point to any other point? Is there a path in the space of Hamiltonians which doesn't close the gap as I adiabatically move along that? If they are, then I say that they are topologically equivalent, and that is what is discussed here. So two H1 and H2 are topologically equivalent if I can take from GS1 to GS2 without closing the gap. Right? And I shouldn't be in the same symmetry class. I shouldn't go out of the space of Hamiltonians. Right? Okay. All right, so the answer to this question is actually very beautiful, right? And this is what was discovered by Kitaev, Ryu, and co-workers. So let's just focus on class A, which is kind of simple to discuss. So if I take any particular value of k now k lives in the d-dimensional torus, remember. If I take a particular value of k, there are LU occupied orbitals, LO occupied orbitals, and LU unoccupied orbitals. So what is the ground state? The ground state is a slated determinant of the occupied states. But if you think about this, if you give this as a homework problem in a course, you will find that people will start putting arbitrary phases on your block states. So they may come up with apparently different answers. But you see, or not, that gauge freedom that they have in choosing the phases of the block states should not enter this discussion at all. So what you realize is, you have to remove that gauge freedom that you have. So if you think about this, you will realize that at a given k, the set of all possible things you can do to mix the set of states there is UL. So from UL, I have to remove mixing the occupied states and mixing the unoccupied states. So I have to quotient UL by this object. So what am I doing here? The state that I am attaching at every point in k is actually an element of another symmetric space. This is actually a symmetric space. So the set of occupied k states at a point is actually a symmetric space. And if it is some other symmetric class, this object will be some more complicated stuff, but it is a symmetric space. So what do I have? I have a map from the d-dimensional torus to a symmetric space. Which symmetric space? Which is determined by one of the 10 symmetric classes. And how does it become the symmetric space? Because I have to remove the gauge redundancy or the phases, the extra phases that I have. Okay? So what is the problem? The problem is to classify this. So by the way, for this UL, this is called the Grassmannian now, that's just technical, right? I need to find the homotopy of maps from the d-dimensional torus to symmetric spaces. So now you will say, okay, this is a problem in math. Okay. So it turns out that this is not such an easy problem, right? So what I'm showing you here is simply homotopies of spheres, bispheres. Remember, my homotopy, my base manifold for the start, my map starts from TD, not the sphere, right? So suppose I were to do homotopies from spheres to spheres, it's actually pretty complicated, right? So if you just took pi 14 of S4, look at this. It's some horrendous group, right? However, you notice something very beautiful, right? If you keep this thing small and run this, you see that things simplify. It's either Z or Z2, right? So what is being stated is, if I run the number of orbitals to very large, some magical simplifications take place. And this is related to what is called as Bott periodicity and all that stuff. Yeah. Right? See, magical simplification take place, and that has been worked out. And the beautiful thing that Kitaev did was he actually showed that this, the homotopies from tori, d-dimensional tori, can be written as some direct sums of some groups of spheres. And then he was able to use known results and then get the classification. And that simplified thing, yeah. No, that's a good point. But you see, so suppose I had these set of occupied orbitals, right? This is set of occupied orbitals and unoccupied orbitals, right? So your point is that, oh, these are of different energy, and therefore, I should be only multiplying by phases of these guys. But actually, if you think about this, you can mix yeah, okay. All right, okay, so that's the answer. Okay, Bhaskaran, your molecule is just showing up, right? Okay, so this is where this stuff comes from, and the fact that these homotopies have this eight, as you run, there's a periodicity of 8, and that's what gives you all this stuff. Okay, all right. So now I want to show you the periodic table for average human beings, right? So all this sounds very fancy, at least to me, And I certainly don't understand it. I have learned how to parrot this out, right? Okay. So I try to make some sense out of this. So the simplest thing is to look at a molecule, right? So a molecule is something in 0 dimensions which has 2 sides, that's the simplest molecule you can construct. And I'm going to put a single fermion in this molecule. So what I'm showing you here is topology right in front of you. So you see, if I'm in class A3, this is the table, it says that, oh, there is no topology possible. How do you see this? So if you're in class A3, because of the symmetry, the Hamiltonian can always be cast in this language, which means the space of Hamiltonians in class A3 is R2, where R2, H1 and H2 are real numbers, therefore R2. So now I take some random point here, 1, and take another random point 2. This is gapped because the eigenstate is plus minus square root of the length here, and I occupy the lowest energy state with my single fermion. There's a gap to excitation, it's gapped. And then I see I can reach any other point other than 0 without closing the gap, which means that every state here is in quote unquote the same phase. Every ground state for all Hamiltonians in the same ground state. Now I impose an additional symmetry and make this into BD1 class. Then what happens? The Hamiltonian is forced to have this structure by symmetry. So now you see something magical happen. If I'm in H1 less than 0, I cannot reach a state H1 greater than 0 without closing the gap. And you also see that there are 2 distinct kind of states possible. Then that's determined by the parity, only 2. And therefore, BD1 is Z2, right? So I hope you understand how you get the notion of symmetry protecting topology. So this is where symmetry protects this topology. And this is the notion of symmetry protected topological phases. Okay, all right, so I hope that this discussion is clear to all, because I think this picture actually gives you the essential idea of what is symmetry protected topological things with just 2 sides. Okay.
I'm very curious with those sides. The fourth one from what?
A2.
2 is that, is it easily described? What is that matter?
2Z would mean, actually it's Z, it means that the topological invariant comes in units of 2. So what this means is the following. So if you have something in that class, and if you had edge states, there will be 2 of them. Okay, all right, so, okay, so like I said, there is a bigger picture which we have discussed in the last transparency. This, okay, I showed you that, this here. So now, what was conventionally called as topological insulators is in class A2 in 3 dimensions, right? So you see that there's something called the Z2 invariant that goes with it. And one of the key signatures of this topological insulator is that if you cut a nice crystallographic surface, then it will actually have a single Dirac cone on that surface, right? And this is what you were asking, is there an experimental signature for that, right? And that experimental signature was actually the first thing to be detected actually. So what is being shown here is angle resolved photo emission, and you can see that this is the dispersion they calculate, and you can, with the caring and loving eyes of a mother, you can actually see the Dirac cones, right? So this is one of the first experiments. Now these things have been done much more cleanly and so on. So you actually see that there's a Dirac cone and so on. Okay, so this is the proof of the statement. Okay, so this is the experimental proof that there is a 3D topological insulator. Okay, I just want to give some broad points about technology and so on. So now imagine that I have a system which is guaranteed to be an insulator in the bulk, but metal on the surface, which is why you shouldn't be changing a light bulb standing on it, right? It actually opens up enormous number of possibilities for technology. Okay, actually, I mean, I invite every one of you to start thinking about what are all possible things you can do with something that is bulk in the, bulk insulating but surface metallic. I'm sorry? No, that you can do even, I don't have any ideas, but you can still invest in me. Okay, so all right, the point is, so just think about electronics, right? So if you take one of these devices, you see you have a silicon based transistor, and then you talk to it with metals, right? There are wires, so there's a technology where you need to put in all this metal and so on. So, right? So you get these channels like this, and you can actually have dissipationless transport. We actually showed E square over H and so on, right? So you can see that this can actually transform stuff. And there is this point that Sumati also pointed out, which is that if you take a topological insulator like the one that we just discussed and bring in some superconductor, then you can actually make a phase with topological superconductor, which has all these Majorana fermions and all that. And then you can use that for, hopefully, for doing some quantum computing, which is protected by, the fact that you're encoding information in these degenerate Majoranas that she talked about, fermion occupied or unoccupied. And so the key point is, we need to find good topological insulator where, quote unquote, there is topology at ambient conditions, like room temperature, okay? And this is not yet achieved, at least in the practical sense. Okay, so we started hunting for these, there was general hunt in this. And so I'm just going to advertise some of the work that Adip did. Where is Adip? Okay, okay, I thought you would have escaped, but okay, all right. Okay, so so the main idea of this is to not particularly to advertise our work. I'll just make a few slides about that, but to show you a different theoretical perspective on topological insulators, right? And that is not from the perspective of band theory, but for the reasons for which Haldane was given the Nobel Prize, which is that he actually a part of the Nobel Prize, which is that he actually showed some physics where something called the topological term renders something gapless, okay? So this entire story about topological insulators that we have been discussing is based on band theory, right? Or states and twisting and so on. There is a different perspective on this, which starts by the statement that a topological insulator in d dimensions is something that is insulating in the bulk, but its d-1 dimensional surface is always, quote unquote, metallic. That means that it has transport without localization. Localization is like disorder localizing particles. So there is a way to ask a question, under what conditions can I have a guarantee that the system is gapless and not localized? You can ask that question in a very generic context, and more broadly you can ask that question in field theory. So the playground to ask that question is this question of nonlinear sigma models. So the simplest example of a nonlinear sigma model is that you write some theory with a vector of fixed length, right? And you say that the vector lives on some manifold. At every point on the manifold you attach this vector, and then you can ask this question, oh, I have some energy which wants these two vectors to be as close to each other at neighboring points on the manifold. That's one of the energies that you will put in. And then of course you will give this thing some quantum mechanics, quote unquote, right? And then, for example, if it is a sphere, if it is running on a sphere, if this does some loop in the path integral, then it could pick up a Berry phase, and so on. And these Berry phases could add from point to point, and you'll get a total term, and that would be topological if that term doesn't depend on the specific realization of the field, but depends on some topological character of this field, like whether there is some winding, no winding, and so on. So such things are called nonlinear sigma models, right? With an additional topological term. So the usual wisdom is the following, that if you can add a non-trivial topological term, then those such terms can actually render the theory gapless. So this is exactly what happens in the Haldane's, the famous Haldane conjecture, where he pointed out that half integral spin chains will be gapless because they have you are allowed to have a non-trivial topological term, whereas integral spin chains, there is a topological term, but it just comes as an integer multiple of 2 pi, which means there is effectively no topological term, right? So then one can actually ask this question, and you can answer it, and in fact you can rederive that periodic table that I just mentioned. So when you start thinking about this, you'll realize that you have to write a field theory. So how do you think about the field theory? So the field theory, if you want to think of this, you say that, okay, there's some UV momentum, and you can say there's a momentum cutoff and so on. So this is what motivated us to start thinking about things beyond the crystalline lattice. So we thought that if you are going to write a field theory, you probably don't need a crystal. So you could actually think of the UV cutoff as some kind of generalized Brillouin zone of the amorphous system, right? And therefore we wanted to see whether we can actually prove this. And this is what Adip did, and he constructed models and actually showed that, yeah. Okay, all right. Okay, that's a fairly okay. So thank you for that question. Okay, so the point is like this. So when you write out theories like this, what you do is you write some theory of fermions in a disordered background, and then what you do is you look at the low energy excitations of these fermions in the disordered background. So you probably know about this. So you can think of the soft modes about the Fermi surface, right? And depending on which symmetry, the symmetry class I talked about, if you kind of do some replica problem and so on for doing the disorder averaging, you will find that these modes will actually correspond to some objects in certain symmetric spaces, which are generalizations of spheres and generalized nonlinear sigma models. Because everything in anything whose target space is a symmetric space, you can write a nonlinear sigma model for. And each symmetry class will actually give you, in a different permutation, different symmetry spaces which are now target manifolds of the soft modes of your, the Couperon and the particle hole modes of your system. So exactly, 2-point correlator in the replica, the full replicas, including the replica indices. No, the bilocal fields will become point fields, right? See, the bilocal of the fermion operator will become point objects, right? When you integrate out the, so you do some, it's okay. I'll just go through some more technical stuff. So what you do is so there's no control in this, but you can do this. So the idea is the following: you disorder average, so you will get a 4 fermion interaction. Now you Hubbard-Stratonovich that and integrate out the fermions. So then those fields are still, in local fields. Yeah, we can discuss offline. Okay, yeah. But anyway, that's the point. That's the overall idea. Okay, so then you can add extra topological terms and so on. And the question you have to ask is, for a given manifold and a target space, which is now determined by symmetries. That's the main message. And you will see that exactly the same Cartan spaces will get repermuted and they will turn out to be different symmetric spaces and so on. So you can ask on a manifold with in which you're targeting, are you allowed a topological term or not? So like very well. So if I have a U1 object, then in 2 dimensions I can have non-trivial fields and so on. Whereas but if I just have like something on a sphere, then I can smoothly deform everything to everything else. So no topological term will be allowed, kind of thing. So depending on what is the manifold and what is the target space, you may or may not be allowed topological terms. So that's the point. And you can ask that question, you can classify that, and you'll actually get exactly the periodic table, right? Okay, so Adip went through this process and he found some very nice things. So the main things that he found was that there are edge states, just like in the usual topological insulator, and he found that when you launch an electron in the energy gap in a finite system with boundaries, you will get E square over H conductance. And then he also had the energy and enthusiasm to go and look at some math kind of literature and discovered this paper which introduced something called the notion of topological invariant without the band structure. And so he adapted this and this is called the Bott index, and he found out that by tuning some parameter, you can actually go to a phase with non-trivial Bott index, and this actually demonstrated that this is truly topological, right? Okay, so what is and the phase diagrams and so on, so things were done. Okay, so what is the idea? The idea is that maybe there is a way to synthetically generate topological materials, which is that you take some 2-dimensional surface and you strew some stuff on it with probably spin orbit coupling and so on. So in some sense, each of these is a GFS like the one that I introduced. So there has enough orbitals and stuff which implements the time reversal symmetry, and then you put them together and they hybridize and they form something. So you could maybe think about doing something like this. Okay. So now, so after maybe 2 years, the experiment is out. So this is a paper that appeared last month. So what they do is they do completely amorphous bismuth selenide, and they actually do RPES, and this is something that I haven't fully understood how, because it's an amorphous system, how exactly that's done, but it's there, and there's a long method section in the paper which I haven't completely worked out. But the point is, they actually see Dirac cones on the surface of an amorphous system, right? So this kind of proof that it is topological, right? Okay. So, okay, so there's some spot size averaging and all they do. So the idea is the following. Okay, this is an interesting question, right? So the idea is that once you disorder average, momentum becomes a good quantum number. So you have to do some tricks. I mean, I actually figured it out. Okay, yeah. I haven't seen anything in this paper, but Adip, yeah. Is there anything? Yeah. No, but did they do transport on the surface? Okay. Yeah. No. That is, see, okay, what is the difference between an experimental plot of conductance and theoretical plot of conductance? Here's a very important point, good question. So you see, when theorists plot experimental plot of conductance, this scale will be linear scale. When experimentalists plot the conductance, this scale will be log scale. Okay, I'll leave it there. Okay. All right. No, you're asking whether people have actually looked at and found E square over H. So you see, in the first with Shusheng Zhang, there's the other German, what is the name? I forget. Sorry, the HGT wells. It was not perfectly quantized. So now I've seen data from the same group, which is getting very, very close to E square H is close to 1. I think it's like, the thing is like between 0.01 and plus minus 0.01. It's actually getting very good now. So now they're getting much better. So it's clear that there are material problems, and there are also problems in connecting and some other issues which they're trying to figure out. But it's been improved quite a bit. They're beginning to plot it on the linear scale. Okay, I haven't seen the other one yet. Okay. That one I thought was like a roadmap. I didn't see data in that. Yeah, okay. All right. Now I want to tell you something very exciting, which I think is something that's really worth paying attention, particularly if you're coming from material science, technology, and if you have some startups and if you have money to invest and so on, right? Okay. All right. So this is a paper. So you see, we have been talking about, let's move in the space of Hamiltonians, and we have been talking all up in the air and in space, right? So we have to bring this down to planet Earth, right? So it's not a good idea to start saying that, I'm going to do some engineering of my Hamiltonian by doing something. What is the best thing you can do? Can you change the phase by applying some electric field or a magnetic field so that you can actually tune a knob to do, right? So lots of people have had these ideas in the past. It's not that this paper that I'm showing you here is the first one. There have been many, many proposals of how to try to change topological phase by applying electric fields and so on. There have been many materials tried and so on, but these folks, they actually sort of did the experiment with this material, which is actually has its own interesting character when it's a 3D system. But when you look at this in a few layers or a mono layer or a bilayer or something, then it turns out by applying a vertical electric field, you can actually change it from a trivial to a topological insulator. So what is the use of this? Tremendous use. So imagine that you create this kind of a device where, this, by the way, this picture is not from this paper, I just lifted it from Google Images, right? So imagine that you have this piece, which is the material that you have. Imagine that you could apply an electric field and change this object to a topological insulator. So what would happen is that you actually get transistor action, you see. So you can see that you can actually drive a current through this edge states, which is now dissipationless, right, by applying an electric field, by turning on or off an electric field, right. So this is the fantastic thing that happened here, and they claim, there's some discussion in this paper about ultra low energy electronics and so on. And in fact, I found that once this kind of papers appear, there are a lot of other sort of science, newspaper kind of people who write about this. There are couple of articles, one in physics.org, which actually had a very nice discussion of how much power can be gained, and there is a whole estimate of if the technology were to go, what would happen, and so on. Very, very nice analysis. All right, so that's good, because I think I think it won't be a far cry to say that most of us are theorists, right, here in this room, right? So then it's also, we can also, okay, all right. Okay, so I have not discussed many things, and much of this is in common with what Sumati said. Sumati talked about Floquet systems, which I didn't even mention here. But I really want to point out some other thing. So this topological bug is not just with the electron people, right? So now people have actually discovered that optical systems, like you create some waveguides and you create some optical, you can create various things. You can have topology in those systems, right? So you could actually direct light to move on the surface of something. You could do all sorts of fantastic things with this. So that has been done, and there's a whole literature on that now, a whole literature. Right? Then mechanical systems, right? You can actually put together things and you can create various topological things out of mechanical stuff. Magnetic systems. So what is this magnetic story? So you see, if I have a magnet, if it breaks a symmetry, then and it's a continuous symmetry that's broken, so you can have magnons. So these magnons actually can have topological bands. So you can have topological magnons and so on, right? So this is now, it's in here to stay, as Sumati pointed out, right? Okay, so what are some of the key open questions? Okay, the key open question is the following. This whole discussion of tenfold classification, etc., that I just discussed was all based on non-interacting physics of non-interacting fermions. The question is, what happens when interactions are turned on? So that something interesting happens was already pointed out by Kitaev in his famous work. He pointed out that in class BD1, like the SSH that I discussed, Z collapses to Z8, which means the classification becomes smaller, right? And much of this thing is actually understood in 1D, and there is some understanding in 2D, and higher dimensions seems to be an open problem, right? And there have been many ideas of using group cohomology and, fractionalized symmetry, quantum numbers, and there are various things. So I also didn't discuss phases with long-range entanglement, taking phases with long-range entanglement and imposing symmetry on them, and these are called symmetry-enriched phases. So this whole set of things about these kind of things that I have not discussed, which is actually a very interesting topic and something that is absolutely worth getting into, right? So what's the key takeaway, right? The key takeaway is the following. If you look at humanity's evolution as a function of time, every epoch of humanity was governed by a particular phase of electrons, right? So you start with the Stone Age. It was actually governed by an insulating phase of electrons. And then the next phase was by a liquid phase of electrons. And the next phase was by a semiconducting phase, which is effectively an insulating phase, but you make it metallic by some doping or something, right? And no, I don't think he had the advantage of not having a cell phone. Right? Yeah. Sorry. No. Yeah. 2 minutes. Yeah. I'm done basically. Yeah. It's 71. Right? And the next age, the AI age, is going to be governed by this. Because once you get these materials in and you can make it ambient, then quantum computing starts. You have ultra high energy electronics, and everything is going to be AI. There won't be any talks. Everything will be given by machines. I don't know what's going to happen, but that's where we are. This is where we are headed. So she who makes the first topological ambient material will govern the world, right? I mean, that's for sure. I mean, if you can crack this, it's for sure it's going to change everything, right? Okay, so that's the summary, and I think if you're doing anything other than condensed matter physics, my condolences to you. You should actually shift to condensed matter physics because this is the best thing to do now, right? Okay, and if you're a material science person or trying to develop materials, I think, it's the time to get into this and really, develop some materials that can do this at ambient conditions. So let me stop there.